Today's topic is very exciting. This is the cross section of the climate science, meteorological data, agriculture, and that kind of soil science and breeding data science. We are going to talk about the very important component in meteorology called evapotranspiration. We're also going to talk about the how the crop type and growth stage can change this study and analysis called crop factor. We're also going to see how remote sensing can come to help Internet of Things. And I'm going to rather go down into the details, showcase it, and then you can obviously see clearly that's what exactly, what numbers, what millimeter of water requirement is required. And this is another topic for this. We are going to talk about the sustainable water management and irrigation and water supply for a typical horticultural or agricultural arable land. So let's delve into it. This evapotranspiration, these are all we are going to talk about. So combine simply the transpiration from the soil and the opposite. The evaporation from the soil and transpiration from the plant leaves. These are water loss as vapor. So why this is important for us? The reason is we need to know how much water we need to supply. And this is, you may say, like in areas like today's in New South Wales that I'm going to talk about in Griffith, we don't have like that much of water shortage at the very least at the time. So currently we have ample supply and water resources around. But it's not the case. We have the problems back in 2019 as the drought, we have bushfires, pandemic interruptions and hurdles for the water transportation. So many things can happen in the future, say global warming and climate change that can make it like the flooding, and then it's another problem in once it's in the agriculture. So we need to make it more sustainable, not to compromise the resources for the future. So this is the combination of different factors come to play and make the water consumption in turn um, determine how much water we need to supply. We have the humidity, rainfall, temperature, and so on and so forth. These are the water, one of the ways that we supply the water, say once it goes to the wheat, low crops, for example. We also can get help from this drip irrigation around the citrus fields as well. We don't have like the underground water. So let's go down into the details of where exactly I'm gonna showcasing as today's study and go to the exact crop and field and season and growth stage water needs. Then everything would make better sense to you. Murrumbidgee is the area in the heart of the New South Wales. It's also not far away from the Mildura in from the Victorian border. This is I just swapped from the satellite view to the aerial imagery here. So there are plenty of citrus buildings around there. So in this aerial imagery, you can better see like how this field would look like. So not every sort of water supply would be feasible. So practically speaking, we have this imagery, and this is one more thing about in the remote sensing that I would like to talk about with you. You see like one area is shaded, and the reason is not like a synthetic image, it's real, though we have the different timings for and as each time the satellite and or the aircraft passes over the area, we would have different at different times, different dates. Yeah, so you would see different lighting conditions around, or even like the shade or the shadows of the trees may not align. That's the thing. And this is shows like the swath, the one I zoom out, you would more clearly see. What do I mean by this swath? The swath is the each ribbon is called swath. The coverage of the satellite here in this case is like the area covered by the this specific camera of the aircraft. And it's, as you can see, as it passes and visits this place at different times, this sunny and cloudy and lighting condition changes. So I can tell you like they might be at absolutely different times. Either this is in the morning and then the next one is in the afternoon, and so on. So this is what we would like to investigate right now. So showcasing for a citrus tree in Griffith, what is the need for us? Uh, Once it goes to the Griffith, I would like to acknowledge the Wiradjuri people, the traditional custodians of the land on which Griffith city and region stands. I pay my respects to their elders, past, present, and extend that respect to all Aboriginal and Torres Strait Islanders peoples today. They have been here like 60, 40, thousands of years, and some of their knowledge about the land, water, sea, ocean, the atmosphere is more than helpful, more consistent with our evolution. Anyhow, so back to our evapotranspiration and water supply and water management, climate science. This is where we normally um, reserve and store our water. And if it is like a low crop, we can supply it by using this sort of portable sprinkles. But for our case, we need to make some calculations from the Bureau of Meteorology. And I'm going to talk to you about how we can find this evaporation from the soil and transpiration from the plant leaves together, combining the and creating this evapotranspiration, which is super important for agricultural practices. One more thing that I said already is that we ideally looking for a formula. I give you a table. You have your own crop related or field specific table, and then you do the math, simple arithmetics, and then there you go. This much water is required. The thing is, I would like to give you a KC, which is a crop factor, a crop plant coefficient. And this also dictates how much water the plant needs. The other factor is its growth stage. So at the fruit is advancing and development, it may need much more water once comparing with the once it's just blossoming or at the low crops like it is the seedling and establishing or germination stages. So basically speaking, the Bureau of Meteorology or some scientists give us like the reference evapotranspiration. This is the acronym for this term. And then we multiply it by the crop factor, how much water, I mean, crop specific requirements that we have. And this is like the magic. And then you have how much water you need for each plant, and then multiply it by number of the plants, and then you can calculate how much water you need to transport in this pipe and do the if it is like the drip irrigation, for example. There are so much of uncertainties come to play. For example, the irrigated zones, there might be some gaps, and these gaps might not be as much helpful. I think I had a picture. So uh, the requirements might not be met. So maybe there are some relaxation factors as well. But this evapotranspiration can give us one of the good uh, decent and reliable amount of how much water the farmer needs to supply. So how this works? The Bureau gives you the wind speed, temperature, humidity, and solar radiation. And why they are important? It's quite obvious. The more wind speeds pass and the more speedy the wind passes and blows around your plant leaves, the more transpiration. So the plant transpires more water, consumes more and consumes and needs more water, right? Same as the temperature, humidity, I think it has a negative correlation. The more the humidity, the less the transpiration and water vapor and water consumption, so on and so forth. In our government, Bureau of Meteorology, also known as BOM, can help you to access very recent data on the ones that I just mentioned. So if you head over to this website and say go to the Griffith, you will see that all the data is provided there. You just simply just click and then you can access all these data over there. For example, I just downloaded the data for the January just 3 months ago, and then start to do some calculations. Beautiful. The matter is all these data are measured around the airports, which are quite important for every city, as I stated in one of our previous episodes. And they can be our resource, for example. So we need to have some more local sensors, Internet of Things, and so on to more further localize. But anyhow, this is what I'm talking about. Just ignore this red box. So this all data measured in January beginning to the end, first, second, and third. You see some data is missing because we missed the relative humidity, for example, minimum and maximum, the wind speed readings as well. And that's the reason why we couldn't make the calculation. So having all these, we have like a formula that I'm not gonna show, go to that one, called Penman Monte to find the and calculate the a reference or grass reference evapotranspiration, and which makes like this parameter. Otherwise, if you are going to do super accurate reading, we have to go to lysometer. Lysometer is simply a device that's unlike the barometer that will be filled with the rainfall water. It will lose water and we measure that loss. It's a very accurate method. So the more the grass soil under a controlled condition for the measuring the water loss and vapors and evaporation or transpiration, the more the water is lost, the more the evapotranspiration is. And it's very accurate, but barely you would see that unless you have a greenhouse or something. And speaking of greenhouse, you see that the data from the BOM, the Bureau of Meteorology, might not be as accurate, or incorporation of them would be not as precise, given like there are not much, there is almost less to none wind speed if it is like a greenhouse. So you need to calibrate it, and it can vary from a factor of 0.3 to even 0.7. As I said, I'm gonna like make it more detailed and make it a use case very clear to you. So say an orange tree, a citrus tree in Griffith, and how monthly it can change due to its growth or fruit stage at different days, for example. So if it is in July, for example, in Griffith and at dormant stage, we expect a crop factor I mean by crop factor is the citrus factor, citrus tree factor or coefficient of 0.4. This should be multiplied by the reference evapotranspiration, which is 1.2 millimeters per day for the grass. And then this is the requirement per day. So if it is like not daily irrigation, if it is in a week, for example, which is maybe 2 days or every other day, you need to multiply it by 2 or 3. So for example, in 2 days, you need almost 1 millimeter irrigation. But you see like this, as you can see in the figure, in January, it grows. Why? Because it is the fruit growing time. So the factor is increasing. Also, given like there are so much, it is the middle of the summer. Ironically, we have the larger reference evapotranspiration. So you see it increases to all the way to 7.2. It's clear, I think, in the figure as well. And then while you do the harvest and the fruit is picked up, and this citrus either as orange, mandarin, or lemon fruits, they are quite juicy, so they consume considerable amount of water. So I hope this table also makes sense about why we do need evapotranspiration and how climate science and meteorological data, agricultural productivity, sustainability, and water management come across and meet at this point for this term evapotranspiration. So I'm going to conclude our presentation using this image, how the crop factor in Griffith for a citrus tree, the green line, may vary against the reference. So in January, we have the hottest days, so we have the hottest evapotranspiration, the most water loss and consumption and vaporizing. Whereas like in the July, which is and June, middle of the winter, the beginning of the winter in southern hemisphere, we have the minimum. And so is the crop factor as well. Thank you very much for watching.